Okay, folks, we'll get started. So I wanted to start today. I was going through the calendar, and it occurred to me that I'm going to be asking for folks' final project proposals in a week and a half, which is closer than it had occurred to me that we were. So my plan is, I think on Friday, we'll do a lecture of basically just brainstorming final project ideas to hopefully get things percolating in people's brains. But in the meantime, given that we're only, a week and a half or 2 weeks for some of you away from that final project proposal due date, I would start thinking really hard about this. And if you are having some trouble coming up with a project idea, I do on the final project link here, I have a, let's see, thought I had it here. Maybe I don't. There's a little right up here about a strategy that you might consider for coming up with an idea. As I think I mentioned on the first day of class for this class, the final projects in this class are in two sort of broad categories. We have the class of projects which aim to solve a problem of one variety or another. And then we have a whole other class of projects with the goal of using engineering as the mechanism by which you learn about something interesting in engineering or in some other field. And so if you're having trouble coming up with an idea, which is sometimes hard because it's so open-ended, one strategy that you might consider over the coming week is with your partners, make a long list of all the stuff that you are either interested in, both in engineering and outside engineering, and the stuff that you would be curious to learn more about, both in engineering and outside of engineering. Make a big long list. It can be as eclectic as you'd like, architecture and, I don't know, number theory and Russian literature, whatever. Make this big crazy list, and then if you're still having trouble coming up with an idea, we can in lab or in some other time, we can sit down with that list and think together about projects that you might use to indulge any of those curiosities. It's just one strategy that I've found works relatively well for folks that are having a lot of trouble coming up with an idea. I'll mention too, as I think I discussed in one of the first lectures of this class, there have been some new additions to the Pico family of microcontroller devices. So we've been, of course, using the RP2040 on the Raspberry Pi Pico development board. There is also a Pico W, which is an RP2040 alongside a Bluetooth and Wi-Fi module. And as we get into the final project season, I'm going to give some lectures on that device. If any folks would like to use that device for their final projects, that's perfectly fair game. What that would allow for you to do is build yourself a user interface to whatever it is that you build that's perhaps driven by your phone over a Bluetooth connection or that you might control over Wi-Fi or something. So it opens up those kinds of communication interfaces. The other new addition to the Pico family that some of you may be aware of is the RP2350. This is a different device. It's sort of a development on top of the RP2040. It's similar in many ways to the RP2040, but different in some. If any folks would like to use the 2350 for their final projects, they are very welcome to, with the slight caveat that it's slightly at your own risk. Many of the things that we will have discussed in this class apply just as well to the RP2350 as they do to the RP2040. There are some differences. And so if you choose to use the 2350, just do so with the understanding that our ability to consult on bugs that you may encounter will be slightly less because we've just have less practice with that. But it is available. I have at least a handful of them for folks to use, and I can, of course, buy some more. Some of the differences that you may be interested in as they may pertain to your final project ideas is the 2350 is faster. You have a faster clock. You have more PIO. You have more SRAM, more DMA channels. There's more of a bunch of stuff. But the fact that the clocks are a little bit different means that if you wanted to use it to do, say, a VGA project, you would have to adjust that VGA driver to be compatible with the 2350. All very doable. Just, warning you that some of the infrastructure that you may be used to just using for the 2040, you would have to adjust for the 2350. Any questions? So like I said, I think Friday we'll just brain dump a bunch of sort of final project hallucinations. The other thing that I'll just direct you to that I strongly encourage that you take a look at this week is here on the course homepage, there's two links. This is all of the RP 2040 student projects that we've had for the past few years. There's a bunch of stuff here. It's interesting to just go through, and it might get your wheels turning about stuff that you might like to do. And then associated with each of these final projects is a demo video. So if you prefer, you could also go through this playlist of student project demos to also get some wheels turning. And so, like I said, we'll talk more about project ideas on Friday. If you would like to come on Friday with any ideas to propose and discuss as a group, that would be perfectly okay. We could certainly do that. Any questions about that stuff? Okay. Yeah, Bruce. Yeah, that's a really good point. I do not put off thinking about your final project ideas because it is in fact a big commitment. You're choosing to work on this thing for 5 weeks. And as Bruce suggested, if you take some time to find an idea that you are deeply enthusiastic about, your experience of the final project will be awesome. If you put it off and you end up just sort of scrambling and figuring, I will do this, it makes those 5 weeks very painful, right? So try to take some time to figure out what you're actually interested in working on. Okay. Okay. So unless there's any other questions about final projects or the logistics of final projects, my plan today is to start talking about Lab 3. Before I do that, is there anything related to Lab 2 that people would like to discuss? I'm very happy to continue to discuss Lab 2 to the extent that it remains useful to people. But we're now in the final week of Lab 2, which means folks are starting to work on Lab 3, so it's about time to start talking about that. Okay, if anything comes to mind Lab 2 related, just let me know. If not, let me then start by just reminding you what we're going to be doing in Lab 3. So I want to just remind you at a high level what the objectives are, what we're going to be building, and I'm going to briefly talk about some of the interesting concepts that you will be exposed to and will have to learn in order to build this thing that we're going to build. And then what I want to spend some time talking about today is one of those topics in particular, because it's most pertinent to next week's checkoff, which is that motor control circuit. So let me just remind you that what you're going to be doing in Lab 3 is building the following. Confirm my age. Hold on. Building the following. Oh, gosh. Let's see. That's okay. I don't need to look at this. Going to be building the following. Here's a schematic picture of it. What we're going to have is an acrylic arm that is clamped at one end to a table. And there's a hinge here at the table, so the arm can swing up and down like this. At the end of that arm, there's going to be a little drone motor. And so you can imagine that when you turn the drone motor on, it's going to generate lift and lift the arm up. When you slow it down, the arm's going to fall back down. And attached to the base of the arm, it moves along with it, is going to be an IMU, an accelerometer and a gyroscope. Your task will be to use the accelerometer and the gyroscope by way of a complementary filter in order to figure out what the current hover angle of the arm is, right? So let's say it's here. You'll look at the direction of gravity as detected by the accelerometer and the rate of movement as detected by the gyroscope and use that to figure out where the arm must be located. You'll compare where the arm is presently located against a user-specified desired hover angle. So you'll build a user interface that allows for the user to say, please hover at 90 degrees. Your complementary filter will detect that you're at 25 degrees or whatever, and it'll compare that difference. And then it will put that difference into a PID controller in order to move the arm to the desired hover location. So it's kind of a version of a drone in which we have constrained every degree of freedom except one. Okay, so we have a 1 degree of freedom drone. This lab is really interesting for a bunch of reasons. One is, you will find that this simply does not work if your control loop is under some rate. We're going to have our control loop running at a kilohertz. But a really interesting experiment that I'll ask all of you to do is when you're building the circuitry here, before you even plug in the RP2040, you can use a function generator to make sure that your motor control circuit is working right? Send a PWM wave in and make sure that, as you turn up the duty cycle, the motor spins faster and so forth. What you will find is that when the arm is beneath horizontal, you as a human being, twiddling a little knob, you'll be able to control that arm to any old angle that you want, under 90 degrees, if this is 90 degrees. And the reason for that is down here, this is a nice linear control problem. You turn the motor speed up a little bit, and the arm goes up a little bit. Turn the motor speed up a little bit more, the arm goes up a little bit more. Once you get above 90 degrees, it's a different story. Because once you get above 90 degrees, if you turn the motor speed up just a little bit, it's going to go near and fall over backwards. And so as the arm gets higher and higher and higher, the control problem gets harder and harder and harder. And so one of the things I will ask for you to demonstrate at the end of this lab is to please show me the highest angle to which you can control this arm. Now, I mentioned an interesting experiment is before you integrate this with the RP2040, when you're just testing the motor control circuit that we'll spend today talking about with the function generator, try to control it past 90 degrees. And what you will find is you simply cannot. Once it gets above about here, you as a human being will not be able to control it anymore because you are not fast enough. I will remind you of a bunch of the sort of control theory concepts that underlie this. But what's actually happening there, the consequence of you not being fast enough is you're introducing phase into the system. And as you go higher and higher, your phase margin is dropping and dropping and dropping and dropping. And as soon as you pop beneath stability, the game's over. And you will find that you just can't do it. And so it really drives home the necessity of a very fast closed-loop controller in order to get this thing to work. Another interesting feature of this lab is I can almost guarantee you that in terms of number of lines of code that you write, this will be the shortest, probably by a lot. There's not as much code associated with this lab as there is with the other labs, though I contend that this is the most challenging lab because it incorporates a bunch of other stuff. I've mentioned a few times in this class that one of the things that's so interesting about embedded systems is that it sits on the interface between the computational world and the physical sort of natural world, and that your debugging environment includes both worlds. And you've kind of sort of been exposed to that in the previous labs in terms of like button debouncing, for instance. This lab, your debugging environment sure includes physics. And if you are not, I've been trying to harp upon good breadboard discipline in previous labs because it's good practice. In this lab, if you do not abide by good breadboard discipline, it will not work. Your project simply will not work because your very high-speed digital motor control signals, they're oscillating voltages on and off, that's generating fields that can mess with the signals you're getting back from your sensor to determine the arm angle. You introduce too much noise on that, and the whole system breaks. So this lab is really interesting in that you can have perfect code, you can have a perfect schematic, but if you are not thoughtful to the physical layout of your system, it still won't work because physics will intervene on the system. Yes?
Random question. When you get above that 90, so you said beforehand when we're debugging, you'll test out on a motor, and you'll be able to use the PWM signals. But once you want to test above that 90-degree threshold and see it's actually working instead of like hooking up and it randomly goes and like or something like that, how do you actually debug/test that?
So you will confirm the correctness of your motor control circuit basically below 90 degrees.
Gotcha.
And then in order to control it above 90 degrees, you will require a high-speed controller coming from the RP2040.
Gotcha. Thank you.
Yep. Any other questions about the objectives here? About what we're trying to build or how we're trying to build it. I'll mention too, so in terms of concepts that this will introduce you to, the IMU with which we're communicating happens to be an I2C device. I chose it for a number of reasons. It is as accurate as we require for it to be. It's also chosen because it's an I2C device, and we haven't discussed that yet, so this is our opportunity to talk about I2C communication. We're of course going to talk about PID control. We're going to talk about this in sort of two ways. I'm going to talk about a very the word I like to use is phenomenological way to tune your PID controller, something that's sort of just observation-based. You turn this parameter up too much. Here's what you should observe happens. Turn it back down a little bit more, then you go to the next one. So sort of a systematic way based on observing your system to get this thing tuned. But then I'm going to remind you about some very analytical background of PID controllers to connect what we're observing to the math that you would have probably seen at some point. Bode plots, that kind of thing, phase margin, gain margin. What I'm going to talk about today, perhaps into Friday, depending how things go today, is electrical isolation of DC motors. I'm going to talk about this a lot more. In short, DC motors create a tremendous amount of electrical noise, stupendous amount, at frequencies all the way up to RF. If we are not careful about isolating that motor electrically from our sensors and from our microcontroller and from the other stuff in our system, that noise can, at best, cause weird malfunctions, and at worst, turn your microcontroller back into sand, right? And so we need to electrically isolate this. We're going to have a long conversation about that. We're going to isolate it by way of these interesting devices called optical isolators. The control input into our motor is going to be a PWM signal, so we'll talk about how pulse width modulation works. Probably review conceptually, but specifically for the RP2040, we'll talk about how that works. You're going to figure out arm angle by way of a complementary filter. I'm not sure, have folks been exposed to that before? Perhaps in fast robots, maybe you talked about complementary filters. In any case, if not, I'll remind you about them or introduce them to you. We're going to be talking about gyroscopes and accelerometers. Discussion of gyroscopes requires a discussion of gyro bias. As many of you are aware, gyros walk around, and we need to account for that. You're going to be doing actual mechanical assembly in this lab. You're going to be building this thing, which, by the way, I have stressed throughout this whole semester the importance of coming to multiple lab sections per week. If you do not do that for lab 3, week 1, I promise you won't finish. I just absolutely promise it. You must come to extra labs for lab 3, particularly for week 1, or you just won't get this stuff built and debugged. We're going to look at some sensor data sheets and then some familiar concepts, UART, VGA, and digital low-pass filtering, which we talked a little bit about. Okay, so it's a great lab to the extent that, you know, this being a CDE class, a cumulative design experience that's supposed to incorporate a bunch of concepts into projects. I love this lab for that. This incorporates just a ton of great stuff that you would have seen throughout your undergraduate curriculum into one tractable but challenging control problem. Okay. Any questions from folks about what Lab 3 is, how it works, why it's interesting? I'm going to start talking about one of these things in particular, if not. In particular, electrical isolation of DC motors. Okay, so I want to talk about, what I would like to talk about is one of the things that you'll be building in lab this week is this circuit for controlling the motor. I want to talk about every element of this circuit. This circuit looks the way that it does purely to isolate that motor from our microcontroller. In order to understand why this circuit is the way that it is, we need to understand what the noise looks like coming off of this motor and where it comes from, because it's only based on that knowledge that we can build a circuit that correctly isolates and protects the rest of our system from it. So this is what we're going to come back to. In order to talk about electrical isolation of a motor, noise isolation from a motor, we need to talk a little bit about how these motors actually work and the source of noise in them. So I'm going to do that first. Let me just mention incidentally, you are going to be building this circuit not on a breadboard, but on a solder board. So you'll be soldering this circuit. This is one of the reasons that I'm encouraging folks to come extra time this week, because that takes some time. The reason we're putting this on a solder board is last year we didn't, and we melted every breadboard in the lab. Because these motors pull about 2 amps. Turns out 2 amps through a breadboard will melt the breadboard. And so this year we're asking for everyone to solder their own motor control boards, which is good practice in any case. It's good to do some soldering in this class. Makes that little board very reusable. So if anyone wants to build a robotic final project that controls motors, it's pretty darn handy to have your little motor control board ready to go. So So in any case, you'll be soldering this, but we'll get to that. So let's talk a little bit about motors. And I want to talk specifically about DC motors. There are, of course, a variety of flavors of motors. I'm going to talk about DC motors, and even more specifically, I want to talk about brushed DC motors. That's the kind that we're using in labs. That's the kind that I want to talk about. So how does a motor actually work? Again, this maybe is stuff that you've seen before, but perhaps it's been a while. The way that a motor works, it is essentially, it will contain two magnets. They may be permanent magnets, they may be electromagnets. But these magnets set up a static electric field. And then inside of that electric field, there's a coil of wire here called an armature, through which we, when we control the motor, put some current. So there's current going through that coil of wire there. You will remember from E&M, probably, that if you have a current carrying conductor in a magnetic field, it will feel a force, the Lorentz force, right? So we're sending current this direction through this armature. It will want to rotate up to align the magnetic moment of that armature with the magnetic field. Now, of course, there's a problem here, which is once we get to the top and we're aligned, well, there's no more force anymore, right? So we have to reverse the direction of the current through that armature in order to keep it rotating. That problem is solved by this device, which is called the commutator. You can see there's a little gap here, and by way of brushes, this is what makes this a brushed DC motor, there's little electrically conductive brushes all the way along this commutator to maintain electrical contact, but the armature can spin on top of that. And so as this spins, when this side is connected to this half of the armature and this side is connected to this half of the armature, the current goes in one direction through the armature, this side of the commutator, that is. When it rotates such that this is connected to this side and this is connected to this side, the direction of the current flips, and so the force felt by the armature keeps it moving in the same direction. It's pretty darn clever, right? And so this automatically, by way of a physical mechanism, handles the direction of current swapping through that armature. Anything else I want to mention about this? One of the consequences of this, what we're going to talk about in a moment, is what sort of a appropriate model for a motor is, right, electrically. And the claim that I'm going to make is a DC motor is reasonably well modeled by a resistor in parallel with an inductor in parallel with a generator. The reason there's a resistor there is because there's some resistance through this whole thing. The reason there's an inductor is there's those loops of wire in the armature which has some inductance, something probably on the order of like a millihenry. There's a generator too. Why would there be a generator included in our model for the DC motor? Well, when this thing's rotating, what we have is a conductor moving through a magnetic field. We have a loop of wire rotating in a magnetic field. That is what a generator is. And so as we start spinning this thing up, the motor itself generates a back EMF, generates an opposite polarity voltage that when it's running in steady state will about match the voltage that we're applying to the motor. This back EMF generally it acts like a automatic current regulator. Okay, so let's say that our motor, we've applied voltage and the motor is spinning at some rate. Spinning at a constant rate means that we're applying some voltage that's getting the armature rotating. As the armature is rotating, it's having a current induced on it in the opposite direction, a back EMF induced on it that will about match the applied voltage. Let's suppose that we grab the output shaft and slow it down. Well, the consequence of that is going to be, because we've slowed it down, there is less of a back EMF being induced onto the armature, which means more current can be put through the armature, more of our applied current can be put through the armature, the consequence of which is the speed reduces, but the torque increases. So you can feel this with a DC motor. If it's running and you grab it, it will slow down, but you can feel that it gets torqueier. And then the opposite's also true. If you hold it for a while, so now it's running at a steady speed, right, and you let go, suddenly you make the trade-off in the opposite direction. The torque out of the motor will drop, the speed increases. So this back EMF it's sort of an automatic regulator for current and torque. The other kind of interesting thing to just note here, may have occurred to you that depending on the position of this armature as it rotates, there's going to be an orientation at which the torque felt by this armature is at a maximum, and a location at which the torque felt by this is at a minimum. And indeed, that is the case. If you were to plot the output torque of one of these DC motors over time, you would see it ripple. You get torque ripple out of these DC motors. But like I said, this generates just a tremendous amount of noise. So where's that noise coming from? Well, one of the places that it's coming from is all these little bristles, right? As the electrical connection with each of these little bristles is made and broken and made and broken, that's generating noise up into the RF ranges of the spectrum. It's generating noise at frequencies that are about equal to or of the same order of magnitude as the clock rate of the CPU. You can see this, incidentally, if you get one of those little software-defined radio dongles, right, and that just allows for you to look at the spectrum, and you plug in a DC motor, you'll see the whole spectrum go whoop. There's noise generated the whole way across the spectrum by these things. The really high frequency stuff coming from the bristles on this commutator. But then there's other noise as well. The direction of current through this is switching very quickly. This is an inductor. Who remembers the equation for the voltage across an inductor? LdIdt. Man, when this thing's spinning and the current swaps direction, that is a huge dIdt. And so even for tiny little L's, millihenry L's, the dIdt is so big that the voltage that comes out is huge. And even worse, this being an inductor, the voltage that comes out is the opposite polarity. And furthermore, we're controlling this motor by way of a PWM signal. So effectively, we are adding and removing power from this thing very quickly. That too is a big dIdt through this thing, which generates a huge L. So how big is the voltage that we could actually expect coming out of this thing? Well, like I said, we can approximately model a motor of this design by a resistor in series with an inductor in series with a generator. So you ask yourself, when we open a switch here, say by way of a MOSFET in our motor control circuit, right? So our PWM signal is opening and closing this switch. Let's suppose that our motor has an inductance on the order of a millihenry-ish. And let's furthermore suppose that we can open that switch really quickly, on the order of like tens of nanoseconds, perhaps, right? It's a MOSFET. We can open and close that really, really fast. Well, the amount of current going through this motor when it's running full tilt is going to be at least an amp. In fact, it could be a bit more than an amp. So you do the math here. 1 millihenry, you're switching the current through that motor. It's an amp's worth of current in a few tens of milliseconds. You're looking at voltage spikes coming out of this thing that are just huge. And opposite polarity. That is sufficient to really do some damage, right? So we really have to be cognizant about the noise that this thing is generating and how to mitigate it. So it's in order to protect against this noise that the motor circuit is the way that it is. What I'd like to do now is build that circuit up one component at a time so that I can speak to here's why this component is here and here's what it's protecting against, here's why this component is here and what it's protecting against, and so forth. So one of the components that we saw in that motor control circuit was a diode. And the diode, you may notice, is in opposite polarity, right? The diode points from the low side of the motor to the high side of the motor. The reason for that is because of those huge LdIdt voltage spikes that we will expect to come out of this motor, right? When we switch the current here, suddenly and very briefly, this becomes the high side of the motor and that becomes the low side of the motor. we better provide a path for current to flow in that direction that is safe. And that's the purpose of this snubber diode or a flyback diode. The idea here is that when we see those big swaps in polarity and big voltages, this provides a safe path for current to flow in that direction. Does that make sense? There's some other stuff there too, though. You'll notice in the motor control circuit, we also have, in parallel with the motor, a little capacitor. I mentioned that that commutator, the brushes on that commutator, are generating noise up into the megahertz range, very, very high frequency noise. This capacitor is just acting like a bypass cap. It's offering a path for the very, very high frequency stuff to take that is safe. But even so, let me see, I have a little, is it going to let me play this video down here? Let's see. No, it's not. That's okay. On your own time, watch this little video down here. That video has an actual demo of a video of an oscilloscope screen. I apply voltage across a DC motor. You see noise just explode across the screen. And you take a little bypass cap and put it across the motor, and the noise goes zoop. Does not disappear, but it attenuates considerably, right? Because we're allowing a path for that very, very high frequency stuff to take. But even so, there's still a lot of noise here. And so the prudent engineer will completely electrically isolate the motor from the sensors and from the CPU, so that there is no electrical connection whatsoever between your motor and the RP2040. Electrons are not being exchanged. There's absolutely no electrical connection. How do we do that? We do that by way of this device right here, which looks on this schematic like an LED and a transistor. In fact, everything there, the LED and the transistor, is all contained in one little integrated circuit package. That device is an optical isolator. The way that this works is, on one side of the optical isolator, as the picture suggests, you have a little LED. The LED is inside of the little integrated circuit package. But there's a little LED in there. And we drive that LED from the microcontroller and connect that LED to microcontroller ground. So that LED shares ground with the RP2040. But there is no electrical connection between that LED and this transistor, which is in fact a phototransistor. It's a transistor for which we can generate current into the base by way of photons instead of electrons. And so what that means is this whole side of the circuit has a different ground from the microcontroller side of the circuit. Totally different ground. Has a different power supply. In fact, it has two different power supplies to this side of the circuit than the microcontroller. So they don't share power and they don't share ground. They're two totally different circuits, and this circuit, the microcontroller circuit, influences the motor control circuit by way of light. Not by way of electricity, but by way of light. And so that makes them completely electrically isolated. Oh, where'd it go? I'm back. Hold on one moment. And by the way, this whole concept of electrical isolation, it's certainly important for this lab. If any of you have any interest in like bioengineering, you know, the sorts of electronic instrumentation for human bodies, both on human bodies and in human bodies, electrical isolation is of life-critical importance. Does anybody know the amount of current that a human heart can sustain across it before it stops working? Is that right? Do you know? Do you know what this number is, Bruce? 10 microamps. So we have to electrically isolate the microcontroller to prevent the motor from killing it. If you're working on human beings, this whole concept of electrical isolation is just of astounding importance. And the consequences, of course, are high. And the sensitivity of the human body, depending on what you're doing to the human body, to current and so forth, is sometimes unintuitively severe, right? So in any case, that's what this is. It's a 4N35. So this is allowing for us to control one circuit from another circuit by way of light, different grounds. One of the practical consequences of this in lab, you're, of course, as always, going to be using the oscilloscope to debug your circuit. Keep in mind that the ground probes on the two probes of the oscilloscope are internally shorted. And so do not attach one scope probe ground to this ground so that you can observe a signal on this side of the circuit, and attach the other scope probe to this ground so that you can observe this side of the circuit, because by doing that, you are connecting the two grounds of this circuit through the oscilloscope. So with an oscilloscope, you may observe this side, and then you can take that probe off, and you can observe that side. So what else is going on here? So we talked about the necessity for the snubber diode. We talked about the necessity of the bypass capacitor. There's a few resistors over here. This one in particular, you can see that this resistor goes from the base of that optical transistor down to ground. Turns out that this resistor essentially sets the bandwidth of that optical connection there. It controls the rate at which the current induced into the base by the LED leaks off the base to ground. You could imagine that if this resistor were too low, we would not be able to turn on that LED because all the current would just leak off the base here, right? If this resistor were too high, we would drop the bandwidth of that connection. We wouldn't be able to turn it on and off as quickly because it would take a longer amount of time for the current to leak off the base so that we could then turn it on again. So with a 1 mega ohm transistor there, that allows for us to control that 4N35 with a bandwidth of about a kilohertz. We can turn it on and off 1,000 times a second, which, as it turns out, is fast enough for the control problem that we are trying to solve. But it's that device that sets the bandwidth limit for our controller. The RP2040 could perfectly happily run a PID control loop faster than a kilohertz if you wanted it to. Likewise, you could read the sensors at a fast enough rate in order to do that. The rate limiting thing here is that 4N35. But it's fast enough. There's another resistor here, the 10K, right, which is above the, what's effectively a BJT there. That is simply there so that when we turn on that BJT, we aren't shorting VDD to ground through this transistor. Also, the arrangement here of the 10K up there means that when we induce, about 0.7-ish volts onto that BJT, it is saturated on. So we have this in switching mode, essentially. You remember from circuits class, you can put these BJTs in a variety of different modes. We're using that BJT as a switch. And then above that BJT, you can see we're grabbing the signal right beneath that resistor, right above the BJT, and using that as the control input to the gate of a power MOSFET. And you can see we're driving the hell out of that gate. We're driving that gate at 12 volts. So that means when we turn that MOSFET on, it is on. It's this power MOSFET that is modulating power on and off to our motor, right? So when you turn the motor speed down, what you're actually doing there is, of course, you're not reducing the voltage applied to the motor. What you're doing instead is dropping the duty cycle of a PWM wave with which you're modulating power to the motor on and off. You're turning the motor on and off. You're leaving it off more than you're leaving it on, so that the average voltage applied to the motor drops. You aren't actually dropping the voltage, you're just dropping the PWM. It's that power MOSFET that is able to turn that much power, the amount of power going through that motor, on and off at a kilohertz rate. We're driving the motor at 5-ish volts. You could drive it up to like 6 volts if you're having trouble getting things to lift, okay? But 5, 6-ish volts. We're driving that MOSFET at 12 volts. And like I said, all of this will go on a solder board. You will not breadboard this, you will solder board this. Now, what I strongly advise against, do not build this whole thing and then test it, because I promise it won't work. Instead, what I recommend is start by building this bit. Get the 4N35 optical isolator attached. Don't solder it directly. We have those dip sockets so that you can actually, if you blow a 4N35, you can pop it out and pop a new one on without destroying your solder board. But get that prototyped first. Let's see, come back to life. Get this part prototyped first, powered appropriately. And what you should be able to do is, you don't even need the microcontroller in the picture yet. Generate a PWM wave with the function generator, 0 to 3.3 volts, just like you would see coming out of the RP2040, and send it into the low side of your 4N35 LED there. If you probe across these two connections, you should see, if this is working correctly and you're properly turning on that LED, you should see a diode drop there. You should be able to measure the voltage drop across that LED. That confirms, okay, I'm turning on the LED. Then you could come over here and scope this point in the circuit, and what you would expect to see is the PWM wave that you're generating replicated over here, but at a 12 volt peak to peak instead of at a 3.3 volt peak to peak. Something to keep an eye on. Remember too, because we're pulling the control signal from above this BJT, it will be inverted. Yeah.
Is there a reason why you chose to leave it full of this
So this arrangement is to make certain that we have this BJT in acting like a switch.
Yeah, but why wouldn't you do like the full down, like if the BJT breaks, you're just
Why wouldn't you do a pull down from here?
yeah, put the BJT on the high side.
Oh, why wouldn't we put the 10K down below it? If we put the 10K below it, it becomes a unity gain emitter follower, which we don't want. So then the voltage that comes out over here is a function of the current induced here, which is hard to know or estimate. In this arrangement, we get full gain. At the cost of an inverted PWM signal, but the handy-dandy RP2040 has a single PWM control bit that says, oh, please just invert the PWM output. So you just set that bit, and your code doesn't even have to know that there's an inversion there. And you're also asked to include a kill switch so that you can just easily remove power. Any questions about this? So let me just point out, there's a guide here to help you put this on a solder board, which I'll invite you to follow. Has anyone done this yet? Yeah?
I just have a question. Could you explain again, I may have missed it, why we're using a 12 volt power supply for the BJT instead of the 5 volt?
This is,
Drive?
yeah, and correct me if, or add anything that you'd like here, Bruce, but This is to make absolutely certain that this thing is on when we want for it to be on, and then off when it's off. Bruce?
So going to 12 forces it to be solidly on. Now you, the separate question is, oh my gosh, the gate voltage is higher than the drain. Does that hurt that? Again, the data sheet says it can be 20 volts higher. Let's say if you want to mess with it, break down the 12 volts to 6 volts, you put it on the FET, and get burned.
Other questions about this? So again, please start working on putting this together before the start of your scheduled lab section, because I don't want people to end up stressed in lab trying to debug this, solder board circuit. And that gives us time to, help you debug it when something goes wrong. Bruce? And there's only 6 solder stations, so don't wait until they're a highly contested resource. Come when you can sit down and put in some headphones and do some nice relaxed soldering. And wear safety glasses, please, when you solder. I'll array a bunch of them on the bench. It sometimes splashes. I wouldn't want for it to get in your eyes because I don't want you to go blind, and I also don't want to get fired. Okay, any other questions? So I'll just point out the other thing that you'll be doing in lab this week, in addition to building that circuit, is doing mechanical construction of this ARM system. This is mostly directions following, but I just wanted to, let you know that this is also something you'll be doing this week. The other neat part of this lab, I'll just mention in the last 2 minutes here, is you're going to build a very cool visual interface to this thing on the VGA, where in real time on the VGA screen, I don't know why the picture's not shown here. That's okay. In real time on the VGA screen, you'll have 2 traces that look like oscilloscope plots. One of those traces will be showing the output of your PID controller so that you can observe the behavior of your controller in different conditions. If the motor's hanging down here and you command it to go here, you'll see your controller go, right? And then it will settle out to some consistent value to hold the motor at its new angle. And then down beneath it, you'll have another trace that's showing the hover angle, the present hover angle of the arm as calculated by your complementary filter, alongside the desired hover angle of the arm as specified by the user. And what you'll observe when your PID controller is fully tuned is you specify a new hover angle, right, which pops that desired angle up to some new value, and the arm angle will go up, maybe overshoot a little bit, and then settle out to exactly bang on the user specified angle. No steady state error, exactly what you've asked for. That's a goal, I think, for next week. That's a good piece of infrastructure to get in place early because it really helps you debug the controller if you can see what it's doing. And so we build that first and then get the controller tuned. Okay. That's it for today. I will be in lab this afternoon. I'll see many of you there. I'll see the rest of you on Friday, where I plan to have a brainstorming session about your final projects.